A geometric understanding of the derivative. If f of x is equal to x squared, then why is the derivative f prime of x equal to 2x? Well, we can derive it algebraically using the power rule. Now, in general, the power rule says that for some differentiable function f, if x is raised to the power of n, then the derivative is the power n multiplied times the base raised to the power of n minus 1. And so as for our example, we multiply the base by the exponent of 2 and subtract 1 from the exponent and call the result f prime of x. Now, it'd be nice if we can understand this more visually, so let's start with relating our function to the area of a square. And so here we graph the function x squared, and we'll focus on values of x where x is greater or equal to 0. And that's because we're dealing with lengths, and lengths can't be negative. So let's define our function x squared as the function that returns the area of a given square with side length x. And so here we have our square, we can compute its area, and we know that the area is base times height, which is x times x, which is x squared, and that's precisely f at x, which is our function. And we can see that exactly on the graph of our function on the left-hand side. Now, what does the derivative f prime actually mean? Well, f prime is the instantaneous rate of change of f with respect to x, which is just a fancy way of saying it's the slope of the tangent line on the graph of f at a particular value of x. That's the slope of the red line. Now, if we relate this to our problem, then f prime must give the instantaneous rate of change of the square's area as the size of the square changes. In other words, how quickly does the area change as the square changes in size by some tiny amount for a given x? Again, that's the slope of the red line. So as the area gets larger, the rate of change of the area is greater, as seen by the steeper slope. So increasing or decreasing the area of the square at this size means there will be a bigger and quicker change in area than when the square is smaller. And so here we see that as the area gets smaller, the rate of change of the area is smaller, as seen by the shallower slope of the red line. Similarly, what this means is that if we were to make a tiny change to the square at this size, there will be a smaller change in area than when the square was bigger. So let's color the square in green, and its area is again going to be given by f at x. That's exactly how we defined it before. And now if we tug on the corner of the square and we increase its sides by just a little bit, by a small amount called h, then we're left with a bigger square, and its area is going to be given by the areas in green, blue, and yellow. And that's further given by f at x plus h on the graph. Now, if we draw a straight line through the 2 points on the graph, the slope of this line is going to give us the average rate of change in area between these two squares. And the slope is the change in y over the change in x. And further, the change in y is the change in area between these two squares. And the change in x is just h. That's the difference in the side lengths of both squares. And finally, that's also expressed as f at x plus h minus f at x all over h. Now, if you've played with derivatives from first principles, this fraction should look familiar to you. Okay. Now let's focus in on the square and derive the change in area, delta area, visually rather than algebraically. Now as before, our function f at x gives us the area of a square with side length x, and its derivative f prime of x gives us the rate of change of the square's area as its length changes by an infinitesimal amount. But rather than infinitesimal, we'll start with a small value called h. There we go. Now what's the change in area as we increase the sides of the square by this h? Well, that's exactly this area. And if we rearrange it, what we're left with is that the change in area is equal to the sum of the areas of these rectangles. And since we know their dimensions, we can compute their areas. And what we're left with is that the change in area is equal to 2xh plus h times h. However, what we're looking for is the rate of change, which is precisely the change in area, delta area, divided by h. And so when taking the areas of rectangles and dividing by one of the side lengths, in this case h, what we're doing is flattening the areas into lengths, one dimension down. Let's have a look at an example so that we understand this a little bit better. So now imagine that you start with this rectangle with a base of 6 centimeters and a height of 1 centimeter. Well, we know how to compute the area. It's just base times height, which is 6 centimeters times 1 centimeter, and that gives us 6 centimeters squared. Now, notice that the units are in centimeters squared, not centimeters, and that's because area is inherently a two-dimensional quantity. And so if we started with area and worked backwards, in this case dividing by h, what we're doing is effectively undoing the process of computing area and getting back to our lengths. And so we would have 6 centimeters squared divided by 1 centimeter, and we would get 6 centimeters. That's not centimeters squared, but that's centimeters one dimension down. And that's the same as the base. And so that's effectively the same as projecting the rectangle onto its base, and what we're left with is a length. Now we could have of course done it the other way, where we started with the area and divided by the base. And so we'd have the same thing, 6 centimeters squared divided by 6 centimeters, and we're left with 1 centimeter, and that's the same as the height. And again, we're projecting the rectangle onto its height this time, and what we're left with is a length. So let's get back to our main example and see how this applies. So what we had is the change in area divided by h, and so now we know that if we take all of these areas and we divide by the height, what we're doing is flattening these areas onto their bases, and we're left with these lengths. The rate of change is therefore the sum of the lengths, and what we have is 2x plus h as our rate of change. Now one very important note is that this rate of change is the average rate of change for some h. It's not the instantaneous rate of change, which is what the derivative means. So what happens when h gets smaller and smaller approaching 0? Well, we eventually get the instantaneous rate of change, and we can see this on the graph that as h gets smaller and smaller approaching 0, the red line segment eventually gets closer and closer to the tangent line. And as we know, by definition, the slope of this tangent is the instantaneous rate of change. Now let's bring back the average rate of change in visual form that we just derived. So the h part of the average rate of change gets smaller and smaller approaching 0, and eventually it becomes insignificant as it vanishes. And what we find is what we initially wanted, which is the instantaneous rate of change. And it turns out to be 2x. That's precisely the derivative. And therefore, the slope of the red tangent line on the graph must be 2x. Again, by definition, the slope of this line is the instantaneous rate of change. Finally, let's see how this relates to our square more visually. So the two lines of length x that sum to 2x are what we discovered as the instantaneous rate of change of a square's area as it grows in size, which is exactly two of its sides marked in red. We'll discuss these in more detail in just a moment. And so what we finally arrived at is that the derivative of prime is 2x, precisely what we got with the power rule. We just derived it in visual form. And again, we only focus on the values of x where x is greater or equal to 0 because we're dealing with lengths. Now visually what the derivative of prime means is that in the limit, the instantaneous rate of change of the area is the addition of lengths, not areas, one on each side of the square. So the instantaneous rate of change is x plus x, which is equal to 2x, which is precisely these two lengths on each side of the square. Again, so note that these lengths are one dimension down from areas. This will become more clear as we'll relate this back to the power rule. And so if we have a square with a bigger side length, where x is some arbitrary length, the instantaneous rate of change of its area as it grows are the lengths added to the sides. Now the bigger square has a higher rate of change than the smaller square, which just means that as the bigger square grows by a tiny amount, its area grows faster than that of the smaller square if the same change in length was applied to it. That's why the rates differ. Back to the power rule. And so because x squared is a two-dimensional quantity, we have two such lengths to add, one for each dimension, recalling that area is two-dimensional and a length is one-dimensional. Back to the derivative, this explains why we multiply the base times the original exponent, in this case 2, and why we subtract 1 from the original exponent, in this case leaving us with 1. Again, it's because we have two one-dimensional lengths to add, one for each of the two dimensions. Now, this extends to a higher dimension as well. If we move up one dimension, our function f now returns the volume of a cube, and following the same logic, we would then have three quantities to add of a dimension less, in this case two-dimensional areas, x squared plus x squared plus x squared, which gives us 3x squared, exactly what the power rule gives us. And so the instantaneous rate of change of a cube as it grows in volume is the addition of three areas, not volumes, the size of the cube's face. And so in general, if f at x is equal to x to the power of n, then the derivative is the sum of n quantities that are of dimension n minus 1, which takes us into hyperspace where we can't quite visualize it. However, we have a geometric understanding of the instantaneous rate of change. Give the next dimension a try and see what you come up with.